Particle decay is the spontaneous process of one unstable subatomic particle transforming into multiple other particles. The particles created in this process, the final state, must each be less massive than the original. Although the total invariant mass of the system must be conserved, a particle is unstable if there is at least one allowed final state that it can decay into. Unstable particles will often have multiple ways of decaying, each with its own associated probability. Decays are mediated by one or several fundamental forces. The particles in the final state may themselves be unstable and subject to further decay. The term is typically distinct from radioactive decay, in which an unstable atomic nucleus is transformed into a lighter nucleus accompanied by the emission of particles or radiation. Although the two are conceptually similar and are often described using the same terminology. Probability of survival and particle lifetime. Particle decay is a Poisson process, and hence the probability that a particle survives for time t before decaying is given by an exponential distribution whose time constant depends on the particle's velocity. P t equals E minus T slash gamma tau. Display style P T equals E caret T gamma tau. Closing curly bracket backslash. Closing curly bracket. Where tau, display style tau, is the mean lifetime of the particle when at rest, and gamma equals 1 minus V 2 slash C 2. Display style gamma equals frac 1 sqrt or 1 V caret 2 C caret 2 is the Lorentz factor of the particle. Table of some elementary and composite particle lifetimes. All data is from the particle data group. Decay rate. Note that this section uses natural units, where C equals 1. Display style C equals HBAR equals 1 backslash. Closing curly bracket. The lifetime of a particle is given by the inverse of its decay rate. Gamma. Display style gamma. The probability per unit time that the particle will decay. For a particle of a mass m and for momentum p decaying into particles with momenta p I. Display style p underscore I. The differential decay rate is given by the general formula expressing Fermi's golden rule. D gamma n equals s pipe m pipe 2 m d phi n p 1 p 2 p n. Display style D gamma underscore n equals frac s left math cal m right caret 2 m d phi underscore n p underscore 1 p underscore 2 dots p underscore n backslash. Closing curly bracket. Where n is the number of particles created by the decay of the original. S is a combinatorial factor to account for indistinguishable final states. See below. M. Display style math cal m. Closing curly bracket is the invariant matrix element or amplitude connecting the initial state to the final state. Usually calculated using Feynman diagrams. D phi n. Display style D phi underscore n. Closing curly bracket is an element of the phase space, and p I. Display style p underscore I. Closing curly bracket is the form momentum of particle I. The factor s is given by s equals j equals 1 m 1 k j. Display style s equals prod underscore j equals 1 caret m frac 1 k underscore j. Closing curly bracket backslash. Closing curly bracket. Where M is the number of sets of indistinguishable particles in the final state, and K, J, display style K underscore J, closing curly bracket, is the number of particles of type J, so that J equals 1, M, K, J equals N, display style sum underscore J equals 1, caret, M, K underscore J equals N, closing curly bracket. The phase space can be determined from D, phi, N, P, P, 1, P, 2, P, N, equals 2, pi, 4, delta, 4, P, minus, I, equals 1, N, P, I, equals 1, N, D, 3, P, I, 2, pi, 3, E, I, display style D, phi underscore N, P, P underscore 1, P underscore 2, dots, P underscore N, equals 2, pi, caret 4, delta caret 4, left, P, sum underscore I equals 1, caret N, P underscore I, right, prod underscore I equals 1, caret N, frac D caret 3, VEC, P underscore I, 2, pi, caret 3, E underscore I, where delta 4, display style delta caret 4, closing curly bracket, is a four-dimensional Dirac delta function. P, I, display style VEC, P underscore I, closing curly bracket, is the 3 momentum of particle I, and E, I, display style E underscore I, closing curly bracket, is the energy of particle I. One may integrate over the phase space to obtain the total decay rate for the specified final state. If a particle has multiple decay branches or modes with different final states, its full decay rate is obtained by summing the decay rates for all branches. The branching ratio for each mode is given by its decay rate divided by the full decay rate. Two-body decay. Note that this section uses natural units, where C equals 1, display style C equals HBAR equals 1, backslash, closing curly bracket, decay rate. Say a parent particle of mass m decays into two particles, labeled 1 and 2, in the rest frame of the parent particle. Pipe P 1, pipe equals pipe P 2, pipe equals M 2 minus M 1 plus M 2 M 2 minus M 1 minus M 2 1 slash 2 M. Display style VEC P underscore 1 equals VEC P underscore 2 equals frac M caret 2 M underscore 1 plus M underscore 2 caret 2 M caret 2 M underscore 1 M underscore 2 caret 2 caret 1/2 2 M backslash closing curly bracket, which is obtained by requiring that four momentum be conserved in the decay. I, E, M, 0, equals, E, 1, P, 1, plus, E, 2, P, 2, display style, M, VEC, 0, equals, E underscore 1, VEC, P underscore 1, plus, E underscore 2, VEC P underscore 2 backslash closing curly bracket. Also, in spherical coordinates, D 3 P equals pipe P pipe 2 D pipe P pipe D phi D cos theta display style d caret 3 vec p equals vec p caret 2 d vec p pipe backslash d phi d left cos theta right backslash closing curly bracket. Using the delta function to perform d 3 p 2 display style d caret 3 vec p underscore 2 and d pipe p 1 pipe display style d vec p underscore 1 closing curly bracket. Integrals in the phase space for a two-body final state. One finds that the decay rate in the rest frame of the parent particle is d gamma equals pipe m pipe 2 32 pi 2 pipe p 1 pipe m 2 d phi 1 d cos theta 1 display style d gamma equals frac left math cal m right caret 2 32 pi caret 2 frac vc p underscore 1 m caret 2 d phi underscore 1 d left cos theta underscore 1 right backslash closing curly bracket. From two different frames, the angle of an emitted particle in the lab frame is related to the angle it has emitted in the center of momentum frame by the equation tan theta single quote equals sin theta gamma beta slash beta single quote plus cos theta display style tan theta equals frac sin theta gamma left beta beta plus cos theta right closing curly bracket closing curly bracket closing curly bracket. Complex mass and decay rate. Note that this section uses natural units where c equals 1 display style c equals hbar equals 1 backslash closing curly bracket. The mass of an unstable particle is formally a complex number, with the real part being its mass in the usual sense, and the imaginary part being its decay rate in natural units. When the imaginary part is large compared to the real part, the particle is usually thought of as a resonance more than a particle. This is because in quantum field theory a particle of mass m, a real number, is often exchanged between two other particles when there is not enough energy to create it. If the time to travel between these other particles is short enough, of order 1 m, according to the uncertainty principle, for a particle of mass m plus I gamma display style script style m plus I gamma, the particle can travel for time 1 m, but decays after time of order of 1 slash gamma display style script style 1 gamma. If gamma greater than m display style script style gamma greater than m, then the particle usually decays before it completes its travel. See also relativistic Breit-Wiener distribution, particle physics, list of particles, weak interaction. Notes J. D. Jackson, 2004. Kinematics. PDF. Particle data group. See page 2. Particle data group. The Particle Adventure. Particle data group. Lawrence Berkeley National Laboratory.